Hi class, this is Mrs. Cribb, and we're going to be going over our notes for Chapter 5, at least the beginning portion, so please pull out your notes. If you don't have them, you'll need to stop the video and go ahead and print them out. So we're going to be talking about the periodic table, and I'm going to be going back and forth between the notes and a couple of prezzies so I can show you some videos that go along with it. And the main thing about the history of the periodic table we're going to cover is Mendeleev, or Mendeleev. I've heard it pronounced many different ways. But credit for developing the modern periodic table goes to the Russian chemist Dmitry Mendeleev, or Mendeleev. This guy, right here, Dmitry, okay? He arranged the elements by atomic masses, though. Now, if you look at your periodic table, you'll notice they're not arranged by atomic mass, and so we'll do a little bit of comparison in a few minutes. Elements with similar chemical properties appeared in the same row. Remember, a row goes this way. And he organized known elements and predicted new elements. And his table was published in 1869. So I want just to get a feel for that. 1869. That's we're into the Civil War at that point. He predicted the spot where gallium should be, because when he did his periodic table, he kind of left some blanks. And then gallium was discovered in 1875. So initially he predicted where gallium should be because he lined up everything up, and people kind of laughed at him because he left holes, but he ended up being proven right. He also accounted for the transition elements, and he came up with the periodic law, at least the old periodic law, which states the properties of elements vary with their atomic masses in a periodic way. Remember, he arranged them by atomic mass, so his periodic law had to deal with atomic mass. So what I've done now is pulled up the Chapter 5 Prezi, and it still is going to cover through the notes. I want to show you a few things. The first thing is it has the periodic table of elements that you need to memorize from the study stack. So if you click on that, it should pull up the study stack, and there it is. And it'll show you all the list of the elements that we're going to memorize, the names and the symbols. And this is not that hard. It looks like a lot, but it really isn't that hard. Most of them are very common. They make a lot of sense. We will actually memorize 36 of these in order, but the rest of them we basically need to be able to say, for instance, that magnesium is Mg, and magnesium will be when you memorize in order, but the ones down here, lead is Pb. You need to memorize the symbol and the fact that Pb stands for lead. So we'll be practicing that a lot. Alright, and whoops, this is the wrong Prezi. Here we go. The other thing, there's a Kahoot that's in this Prezi. You can look at that later for practicing purposes. And then there's another periodic table Prezi. If you click on this, it brings up this particular Prezi, which I accidentally clicked on. The periodic table of elements Prezi. And in this, there are just specific videos. There's going to be a tutorial right here. You don't actually have to watch this tutorial. It says must watch because in the past it was required, but this is going to be a review tutorial about periodic trends. And so if you want to go back and watch it, you can. And there are here two more videos that cover periodic trends. These are much shorter. They give you little shortcuts for periodic trends when we come to that. So we're not going to watch these right now, but those are there for you. And go back to the Prezi, Chapter 5 Prezi. Alright, so there's the periodic table, and we'll be referring to your periodic table that I gave you, that you color-coded. It would be good for you to pause the video and get that out to refer to it at this point. Alright, I'm going to assume that you've done that, and so as we go through, you might need to look at it. Okay, this again is just the notes we just talked about. We talked about Mendeleev, but here I wanted you to see this. This was his periodic table. It was based on what he did, based on his law. And you'll notice, now we haven't talked about Doperian triad, and we're not going to worry about those, but all these ones with this blue shade, those are the elements that he knew about, okay? The pink ones, though, were not there. Those are the ones he predicted that would show up, and there's gallium right there, and remember he put it in order by atomic mass, so notice how the atomic masses are getting higher. So this is the first one that was actually located or discovered after Mendeleev predicted his particular periodic chart. All right, that brings us to the modern periodic law. Henry Moseley, there's him right there, Rutherford's assistant. Now remember Rutherford, he was the guy who his other assistant, Geiger, they all worked together and they figured out that gold foil experiment, and so they figured out that there was a nucleus, and then Chadwick figured out there were protons, and now Moseley, one of his assistants, figured out how to count the protons. So he developed a way to count protons in an atom in 1912, and I think 1912 is right around I think 1912 is when the Titanic sank, isn't it? Yeah, so right around there. And then he arranged elements in increasing atomic numbers. So remember before, they were arranged by atomic mass. That's what Dmitri did, atomic mass. So now we arrange them by atomic number, and we have a new periodic law, the modern periodic law, says that properties of elements vary with their atomic numbers. So before they were arranged by atomic mass, now they're arranged by atomic numbers. So the properties vary in a periodic way. And all elements up through 92 had been found and put in their place on the periodic table by World War II. They had found their place on the table. Then we have a few artificial elements, and experiments with nuclear energy produced heavy elements. In World War II, remember this? We were making A-bombs. And so we started to kind of fuse things together and fizz things apart. So fusion, nuclear fusion, would combine nuclei to make heavier elements. And these elements, artificial elements that we started to make by combining different nuclei, are called transuranium. That means means after. So it's after uranium elements. So they have atomic numbers greater than 92. Neptunium and plutonium are found in very small amounts in nature, and the rest are all man-made. And so here's another picture of a modern periodic table now. So 92 ends right down here. There's uranium. Okay, there's neptunium and plutonium. Like I said, those are little trace amounts in nature, but every number after that, all these are man-made. And you'll notice that these are the lanthanide and actinides. They kind of go right in this area right here. So we get some more down here that are even bigger. And we're still trying to play around with all of these. Okay? That brings us to the structure of the periodic table. In the periodic table, the groups or families go across the top. So, group 1 and 2, 3, 4, 5, 6, 7, and 8. And we talked about those before. And that's the 1 through 8A, that's the North American Convention. And then the IUPAC way is just labeling 1 through 18. Remember, in the middle, it has those B's. And we've been dealing with these already. And I told you there were 2 ways to name it. And so you just need to know that there are 2 ways and how to deal with them. We're mostly going to be using 1 through 8A, but I might also refer to it as 18. So if it has an A or B, make sure you're careful when you look at it. And then if it has just a number, you don't have to worry about that. You'll be able to look at it easier. Okay? So the groups are at the top. Remember, this is group 1. Group 1 elements have 1 valence electron. And the periods go across. The periods correspond to the energy level, the principal energy levels. So this is energy level 1. That's the 2 red. That would be hydrogen and helium. Energy level 2, energy level 3, 4, 5, 6, and 7. And you should have all those numbers on your periodic table. The principal energy levels and the group numbers across the top. Okay? Now also I want you to notice that this is just an entry that a periodic table would have of molybdenum. Molybdenum, the atomic number is 42. That's the number of protons, which is also the number of electrons in a pure element. The atomic mass, which we've calculated using the isotopes and the weighted average. The symbol's in the middle. Okay, I could have zoomed in on that, I guess. All right, now I want you to look at your periodic table and answer the questions that are right here. We're going to figure it out. What element is in group 2 and period 4? Okay, so here's group 1. See the group numbers at the top? There's group 2, or 2A. They put them in Roman numbers. So we're dealing with group 2 and period 4. The period numbers are along the side. We just need them to intersect. So group 2 goes down and period 4 goes across, so that's calcium, Ca. I can zoom in on that a little bit for you. Calcium, group 2, period 4. All right, what element is in group 5A? Now notice it has the 5A, that's one of that North American thing, and period 5. So be careful. This is group 5A, not group 5. There's group 5, but group 5A. There it is in Roman numbers. So group 5A and period 5. Period 5, there's the period numbers. Go all the way across until you find group 5A. It looks like SB, antimony. Antimony is group 5A, period 5. Antimony has 51 protons, 51 electrons in its neutral atom. What element is in group 17? Okay, that's the IUPAC grouping. So now we're looking at the 17. There's 17 or 7A and period 2. So there's period 2, group 17. So that's fluorine. Fluorine with 9 electrons, 7 valence electrons. Because remember, the group numbers can tell you the number of valence electrons. So group 16 has 6, group 15 has 5, group 4A has 4. So remember, that also only works for the ones with the A's. The B's, the transition elements, and these guys down here, the intertransition elements, don't follow that rule. We have to do that electron configuration thing, which we did before. All right, now let's move on. So now I want you to look at these Bohr models of some of the elements. Now notice this will be group 1A, 2A, 3, 4, 5, 6, 7, and 8A. These don't have A's on it, but that's what they are. This is the Bohr model with the 1 proton and the 1 electron in its first energy level. When we go down to period 2, this would be period 2. If you stop and look at your periodic table, find lithium in period 2. It's element number 1, 2, 3. Okay? Lithium has two electrons in the first energy level and 1 in the second energy level. So notice this element on the bottom is bigger than this element on the top because it has 2 energy levels. Period 3 has 3 energy levels. 1, 2, 3. That's sodium. It also still has only 1 valence electron. Each one of these guys in group 1 have 1 valence electron. But their period number tells you how many energy levels. 1, 2, and 3. If you go across over here to fluorine, fluorine's in period 7A, group 7A, or 17, and in period 2. So it has 2 energy levels, 1, 2. It has 7, there's the 7 valence electrons, 2, 4, 6, one more, 7, but 2 energy levels. Chlorine is in period 3, has 3 energy levels, and still only 7 valence electrons, 2, 4, 6, 7. All right, we've talked about valence electrons already, but I want you to see the Bohr models and how, as you add the electrons to the energy levels, it makes the atoms get bigger. So as we go down, we're getting bigger and bigger as we add more and more energy levels. So period 1 has the least amount of energy levels and the smallest atoms. Period 2 is the second least, and then period 3, 4, 5, 6, and 7. And we'll do a little bit together with that. All right. Transition elements are exceptions to the rule about assigning valence electrons. Remember, we talked about that. So now, when you look in your periodic table, what element is in period 2 and is a member of group 15 or 5A? Period 2 and is a member of group 15 or 5A. All right, I'm going to go to the picture we just looked at. Not that one, the periodic table. There it is. 15 in period 2, that would be nitrogen, as long as I didn't forget what I was asking. Okay? And back to the question. 15 in period 2, good. And to what period and group does the element with the atomic number 10 belong? So now I'm going to look at atomic number 10 element and tell me what group it's in and what period is it in. So I got to go back to that periodic chart again. I think I'll just zoom in this way. Takes a little bit longer. Maybe I shouldn't do it this way. So find element number 10. All right, there it is. There's element number 10. Okay, what is its group number? 18 or 8A. What's its period number? Go all the way across. Period 2. So you just got to see where those things intersect. 18 or 8A. And period 2. All right, so that brings us to metals and nonmetals. I'm going to go back to the the Prezi here, not the Prezi, the PDF, and write on it for you. Okay, I'm going to remind you about this. Get a little bit smaller pen. So remember that's group 1, 2, and these are A's really. Group 1A, 2A, 3A, and that's 4, 5, 6, 7, and 8A. All those are A's. And then the period numbers are 1, 2, 3, 4, 5, 6, and 7. Okay? So these things are on your periodic chart that you should be looking at. Here's another picture just to show you how, this time we're going across the chart. So lithium is in period 2. It's in period 2, and it's in group 1. Notice it has 1 valence electron. Boron has 1, 2, 3 valence electrons. Boron would be in group 3A or 13. Lithium would be in 1A or 1. Beryllium, they just didn't do beryllium. Okay? And then carbon would be in group 4A, nitrogen's in 5A, oxygen's in 6A, fluorine is in 7A or 17. So it has 7 valence electrons. Notice 1, 2, 3, 4, 5, 6, 7. Also notice this has only 2 energy levels. This one has 1, 2 energy levels. This one has 1, 2 energy levels. There's nothing in that third ring there. Okay? This one has 1, 2 energy levels. Those are the principal energy levels. Those are the period numbers. So they're all in period number 2. They all have 2 energy levels. Neon, 10 electrons, 10 protons. I could write that here if I wanted to. 10 protons in neon. The first 2 electrons are in energy level 1, and then 8 of them are in energy level 2. Those are the valence electrons for neon. Okay, now we're going to talk a little bit about the metals and the non-metals for how to recognize them on the periodic table. Okay, so let me go back to here for a minute. I'm going to get a periodic table. And here I want you to notice this line, this jagged dark line between this red side and this purple side. Most of the periodic table deal with metals. Hydrogen is that weird thing. Remember, hydrogen is special in all kinds of ways. This is one of those ways. It really could be sitting right over here in column 7. It's a non-metal. And then we have these light purple guys, the ones that are really adjacent to the stair step. Those are called metalloids. And metalloids contain a little bit of properties for both metals and non-metals. So it's important for you to know all of these guys are metals, all of these guys are non-metals. Metals and non-metals, we're going to talk about that a lot as we go through this chapter. And also, this is to show you what the expanded periodic table would look like. So if we put that lanthanide and actinide series in the periodic table where it goes, the F block, this is what it would look like. It would be a little bit more difficult to deal with. It's one reason they squish it and put it down at the bottom. So this is still the S block right here, S. This is the F block that normally sits at the bottom. There's the D block with the 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the P block right here with its 6. All right, before we go on to periodic trends, we got to finish up. So let me look at my notes. I'm going to fill in the information about metals and nonmetals, what I really want you to know. There's several things you need to know about metals. Metals have luster. What does that just mean? That just means they're shiny. And every time I say that now, I hear the song from Moana in my head. Now I might end up singing that in class. Shiny. So metals have luster. That means they're shiny. What else? They conduct electricity and heat. Conduct, not condust. Conduct electricity and heat. They are malleable, malleable, which means you can pound them flat with a mallet. That's how I think about it. You can form it into different things. That's why you can have rings made out of metal. That's why you can coat buildings with gold because it's malleable. You can make fine, thin sheets of it. And they're ductile. And I always think of, okay, ductile, I guess we could say it's like wires. I think about wires and I think about duct work on this in the ceiling. You can pull it to thin wires and think about copper. Copper gets pulled into thin wires. It's not too terribly a different property than malleable. And metals are mostly found as solids, mostly. There are some exceptions to the rule, but they're mostly found as solids. If you look on your periodic table, you will notice a few things that are blue. Mercury is a metal, but it's generally a liquid, and it looks like the lettering is usually blue on the periodic table. Now what about nonmetals? Pretty much nonmetals, they're in groups 14 to 18, and above that stair step, so we have that stair step on the periodic table, so they're up here. Okay, and they're pretty much everything that metals are not. So they're not shiny. They're not shiny. Just put that. They lack luster. They don't conduct electricity well. Don't conduct well. They are not malleable. They're brittle. The opposite of malleable is brittle. Instead of pounding it flat and kind of squishing, if I pound on it, it'll just break apart into pieces. Kind of think about something that's brittle. Peanut butter, brittle. Peanut brittle is brittle, but maybe think about a sugar cube. If I pound on a sugar cube, it just break apart into lots of little pieces of sugar cube. But it's not exactly the same thing. Brittle just means it breaks easily. It's not ductile, and they're usually found as gases. Okay? Nonmetals are usually found as gases. Now those metalloids, those are the guys that are near the stair steps. Okay? So the metalloids are the ones found in that area, right around the stair steps, a little bit on both sides. They have properties of both metals and nonmetals. Okay? They have metallic luster because they can be shiny, but they're also crumbly and brittle. Instead of being malleable, they're crumbly and brittle. They conduct electricity better than nonmetals, but not as well as metals. And if you look at a periodic chart, you can see some of these. Okay, so I pulled one up, one of those interactive periodic charts, and we can look here. Here's some of the metalloids. See the light green color says metalloids. So germanium is a metalloid. Okay? And this is all about germanium. See how it's shiny? Sort of like the metals. The symbol is Ge. So you can read all about germanium right here. And I want to look at silicon, a non-metal. I'm sorry, not a metalloid. Again, it's shiny. It's also what we do, it's kind of a semiconductor, okay? It conducts electricity only under certain circumstances, so they can use silicon in computer parts. All right, so here, all those light green areas, those are the metalloids. The nonmetals are all over here. We have these guys that are the noble gases. We'll talk about those in a bit. They are very different. But all these guys are metals. And we're going to talk about the specific names of each one and how they work. But if you use this particular periodic chart, and I think I've pointed it to you before, you can just see a lot of good information about the periodic table. Okay, and that will bring us to the periodic trends. And we're going to go through each one of the families in the periodic table in the next video in 5C or in class. But periodic trends are something that we need to cover as well. I'm going to go through them a little bit right here and then also review with you possibly in class. Otherwise, you can just use this as a review. So atomic radius is determined by your electron cloud. Remember the electron cloud, it's the quantum model. And the atomic radius, it starts at larger on the left side and it goes to smaller on the right side of the periodic table. In general, the radii of atoms decrease left to right. As the principal energy level increases, so in a period, I think I may have taken out no, that's not right. As the atomic number, I'm looking at something else, sorry. As the atomic number increases in a period. Because remember, a period goes across this way. So this is period 1 and 2 and 3. The principal energy levels increase as you go down in the group. So that's 1A and 1. So as the atomic number, remember what the atomic number is, that's the number of protons, increases. Now the number of protons is also the number of electrons. So as the electron count and the proton count increases, the outer shell electrons are held progressively more tightly. I'm going to show you a couple of things about that in a minute. And the average distance from the nucleus to the outer shell electrons decreases. Okay, atomic radius increases when moving down a group or column in the periodic table because another principal energy level is added. So those are the two main things you need to know about atomic radius. So let's look. As I go across, notice the sizes are getting smaller generally. Okay? But my atomic numbers are getting bigger. And as I go down, I'm getting bigger. Because as I go down, I'm adding more and more energy levels. Okay, let's think, we got to think about that, why that is. Okay, first we're going to compare, we're going to draw the Bohr model for sodium. Okay, now I'm going to stop and pull up the periodic table again so we can see how many protons and electrons there are in sodium. Okay, sodium, 11 protons, and so 11 electrons. So we're going to draw that. I'm going to draw just 11p to represent the protons and 11 electrons. So the first 2 electrons are in the first energy level. And that would be the 1s. And then I have 8 electrons in energy level 2. And that would be so this is energy level 1, and this is energy level 2. And so we have the 1s covered, and we have, in energy level 2, we have the 2s and the 2p6. Okay? And then, so that's 10 electrons. 10. But sodium has 11, so I've got to do one more electron in the third energy level. So there is its valence electron right there. And it has 3 energy levels. Now let's look at chlorine. Okay, let's compare where chlorine is to where sodium is. So here's sodium in period 3, and we're going to go all the way across. Chlorine is also in period 3. Okay, has 17 valence electrons. 17 electrons, because it's also in group 17. So 17 electrons and 17 protons. That's what I need to put in my picture. Okay, so I'm going to draw again. I'm just put 17p to represent the protons. And then the first 2 are in the first energy level, in the 1s. And then we have 8 in energy level 2. And that would be the 2s and the 2p. In fact, over here, that third energy, that was the 3s1. That was the valence electron in 3s1. So that's now 10, and it has 17. So in the third energy level, it has 7. 2, 4, 6, 7. Okay, those are the 3 energy levels for chlorine. 1, 2, and 3. And it's the 1s2, the 2s2, and the 2p6. Those are the second energy level, and the 3s2, and the 3p5. So that's in this one is those two things, the s and the p's. And notice the valence electron count is the 2 plus the 5. That's 7 valence electrons. Well, let's count them. 2, 4, 6, 7 valence electrons. 7 valence electrons in the third energy level. Okay? Now let's draw the model for potassium. Potassium should be 1 energy level down. Yes, it's in period 4. So it has 4 energy levels, and it has only 1 valence electron, but it has 19 electrons and 19 protons. So I'm going to pause the video and just draw this real quick for you. Alright, I drew it for you. And let's look at this again. We have energy level 1. It covers the 1s2. We have energy level 2. It has the 2s2 and the 2p6. And that's a total of, there we go, 8. 8 electrons in that second energy level. And then we have energy level 3. And that has the 3s2 and the 3p6. And that's still 8 electrons. Right here, 2 plus 6 is 8. So energy level 3, 2, 4, 6, and 8. And then that last electron out there, that one right there, the valence electron, that's energy level 4s1. 4 energy levels. So I'm going down. This sodium was in period 3, and potassium's in period 4. So 4 energy levels. Notice that it's larger in radius than sodium. Okay? All right. Now we're going to draw boron for a moment. Bromine. Okay, bromine. And bromine has 35 protons. So I'm going to draw that one. 35 protons. It's also in period 4, so it's going to have 4 energy levels. All right, you see that? Bromine has 4 energy levels. There's energy level 1. That's the 1s2. Energy level 2. That's the 2s2 and the 2p6. Energy level 3. That's the 3s2 and the 3p6. And energy level 4 with its 1 valence electron. And that valence electron is in no, that's not right. It's not 1 valence electron for bromine. Bromine has to have 7. It has 7 valence electrons. Sorry, I didn't draw the right number. Let me put the right number in there for you real quick. All right, I got it right now. Because I had got to add in all the ones from the energy level 3. So it covered 3s2 and 3p6, but then it covers 4s2 and then 3d10, so that's still in the 3rd energy level, and then 4p, and since it has 7 valence electrons, 4p5. Okay, that was what we covered last chapter. And so I circled all the 3rd energy level electrons for you, because if we add up all these guys right here, all the electrons in that group, that's 2 plus 6, that's 8 plus 10 more is 18. There have to be 18 electrons, and that's what's here now. And then the valence electrons are the outer shell electrons, and there are 7 outer shell electrons, 7 valence electrons, and that's these from energy level 4. Now notice, again, it has 4 energy levels, so it's bigger than chlorine. Because as we go down, this is still in the 3rd period, and this is the 4th period, okay? It's more. Now, that makes complete sense when you go down. But when you go across, when you go from sodium to chlorine, or from potassium to bromine, even though bromine has 35 protons and 35 electrons, and potassium has 19 protons and 19 electrons, bromine is smaller than potassium. Why do you think that is? Okay, we're going to stop and watch a video that might help explain it. All right, first I went back to the chapter 5 notes, and I bring up this little image. And this is an image of putting rubber bands around a container. And the more rubber bands you put around it, the tighter it gets squeezed in the middle. And kind of think of each rubber band as more electrons and protons. The more you have, the tighter it squeezes, the smaller and smaller it gets. So I have a lot more rubber bands, a lot more electrons squeezing tightly towards the protons, and it decreases the size. So when we're in the same period, even though we have the same number of energy levels, as we add more and more electrons, we're squeezing tighter and tighter. Another way of thinking about it is this video about watermelons. Okay, we're going to watch this real quick. So there they are, they're adding rubber bands to a watermelon. You may have seen this on YouTube before. The more they add, the tighter it gets squeezed in the middle. And the tighter it gets squeezed, the smaller the center of the watermelon is going to get. I'm going to kind of, oops, fast forward it just a little bit. It's too far. Oh, there it is. It's about to pop.
I told you it wasn't going to happen.
Now, I just use this as an illustration of how the atoms actually get smaller and smaller and smaller as you add more and more and more. So we just drew the planetary models. Now let's look. Here's the actual radii, or just basically the size of the atoms. They get generally smaller as you go across. Remember, the same period, they get smaller as you go across because I'm adding a lot more electrons, a lot more protons, and they squeeze tighter. Now, why do they squeeze tighter? Remember what I told you before? One of the main things in chemistry, the main things about all of this, that opposites attract. Opposites attract. Remember that? Opposites attract. So when I have a lot more positives and a lot more, see if I have just a couple of positives, protons, and a couple of negatives, they are attracted to each other. But if I have a lot of positives and a lot of negatives, they are really attracted to each other. So the reason it's getting smaller, squeezing tighter, is because I get a stronger positive and a stronger negative, and they're pulling towards each other even stronger. They're like strong magnets. Okay? Now, atomic radius, we're going to, ionic radius, I think we're going to start with the new information on ionic radius and just add to this concept in a little bit. So hopefully that helps you. We will review. So see you soon.